Right. So yesterday we had a look at a small language, and then we gave it semantics. So the semantic of the language was sort of implicit in its definition, and we're saying that, for instance, if you're trying to add a number to a boolean, that's a bad sum and it should be rejected. But that's specific to our setting. And then we describe what it means to be a value of such an expression, and we define an evaluation function using denotational semantics, which is this idea that every constructor in the source language is associated to its meaning in the denotation, like in the domain of interpretation, and the sub-expressions are automatically translated. Like you don't get access to the syntactic description of the source term when you're giving the semantics. And it tends to give like really well-behaved semantics. Then we saw some examples. And what we saw in this evaluation is that, of course, because the source syntax was not preventing you from building expressions that had no meaning, you're forced to have a domain of denotations with an extra value corresponding to just
It went wrong.
garbage.
Yeah.
Yeah. So then we saw how we could prevent that by actually having a notion of type, which is intrinsic to our language. So now we have two notions of types, right? We have the object one corresponding to the object syntax that we're describing, and we have the meta level notion of type, which is the one internal to ACTA. And then we saw we could index expressions by the type of the value they're meant to compute, and that's an object type. And then we saw that we could not even write wrong programs anymore, thanks to all of these constraints.
Yeah.
And yeah.
Stylistic point is just we tend to choose constructor names beginning with a backtick to indicate that we are creating data which are kind of quotations of something else. So this thing is really turning us talking about Nat and Boole into your actual Nat and Boole.
Yeah, so then we could define the interpretation. So again, we're defining the domain in which we are going to give meanings to our programs. But now, because everything is typed, we don't need the maybe monad anymore. Because the well-typed programs, we know they won't go wrong. They won't generate garbage. They will generate a value of the appropriate like meta level type. And then we wrote this evaluation function in the last 2 minutes because it's just really nice. There are no broken cases to consider. Everything just works. Okay, and then we evaluated it on 0 plus 1, and it returned 1, and we're really happy. But how do we know that when we transform this language of expressions into a typed language of expressions, you actually retained the same semantics? What does it mean to have a typed expression compared to the original source expression that was untyped?
Maybe the typed expressions only worked because they were typed. I mean, maybe they did something different because we were staring at them with typey eyeballs.
Oh, yeah.
Yeah.
So to even be able to connect the two, basically we're going to need to express what it means to go from an untyped expression to a typed one, or the other way around. Like, it doesn't really matter. What matters is that we're relating the expressions in both languages to say they are in well, not one-to-one correspondence, but they are somehow related. Oh, it's lowercase t here. Oh, so I've been naughty, but so I want to define this erasure function that takes a typed expression and then forgets about all of the types that were sprinkled on the expression. So just a syntactic thing. This is not pipe. This is not a pipe.
Dear, oh dear.
This is a backslash pipe. Because the standard pipe is used for with like for these extra arguments you're passing to the function. So here Agda will get confused, and instead we have this Unicode symbol, which looks exactly the same, but is not actually the same character.
Yes.
For our
Mathematical notational conventions, it's very often the case that an operator which is spelt surrounding with vertical bars means throw away some information, or measure, or just summarize,
yeah.
forget some aspect of. So here we're forgetting that it's typed.
Yes. So if I have a natural number of type nat, I can return a natural number without any consideration for what the type is. So here I use auto because I knew it was going to pick the first constructor, and now I'm going to stop doing that because it's going to generate garbage otherwise. The Boolean becomes a Boolean, and it looks a bit silly. Oh, actually, I was going to write this, but that's not going to work.
Indeed.
It looks a bit silly because it looks like we're just repeating the same thing over and over, right?
Can you say add query query?
But the thing is that we're transforming constructors to texpr into constructors to expr. So even though they're named the same, because Agda allows us to have this kind of ambiguity, because in a type-directed manner, it can always know which one you meant. We are actually doing some work here. It's not very interesting work, but we are doing some work. So if I try to fit this in, though, we see the problem, right?
So what I'm wondering is, if you say add question mark,
yeah, it's going to work, I think.
And then you say M and do auto, does that do the right thing?
Oh, I see. Okay.
Yeah.
So first of all, it was rejected because the add was indeed the add for expr, but then I tried to feed the M, which was still texpr. But let's see. Oh, yeah. If you put some values in the goal and then you use auto, you're telling it, I would like you to use that thing. So in the first case, it worked. In the second one, it reused M for some reason. Like
alphabetical order.
Addresses like strategy is a lot nicer because it's trying to be.
It should actually be trying to use
maximally using the arguments you give it. So it's all about like how you implement that heuristics. Okay, and ifta becomes ifta, where, well, this one should.
Yeah.
What? Oh yeah, they're untyped. So anything could go in that hole, actually. It doesn't have to be the left branch. That's
Still, at least the edit distance to what you want is small, and it saves you having to type those Unicode pipes.
Oh, no. Okay.
Classic.
Right. I mean, it's unfortunate, but it is indeed ambiguous because it could be. Could it be? I don't know. It's not, right? But it's somewhat non-local because you would need to have something in between here for it to be ambiguous. Anyways, in this instance, Agda is not too happy. All right. It's not the nicest thing, but it will work. All right, so now that we've traversed our expression and we've forgotten all of the nice invariants that we had built in, one thing we would like to say, maybe, is that this erasure makes sense. So, okay, if you eyeball it here, it's you're copying constructor to constructor, so it's maybe not that shocking that it makes sense. But what does it mean for this erasure function to be correct? Well, there are multiple ways to express that. The one here, let's not do this quite yet. One possibility is to say it's correct with respect to evaluation. So correctness is always with respect to some notion of truth, right? Some relation between the source and target.
And this is kind of a normal thing anyway. I mean, the usual deal in typed programming languages is that the type checker gives your program the once over and then outputs some lump of machine code that's got no idea about types. And you generally want the promise that that lump of machine code is going to work. Well, we're in the same kind of situation here. What we want to say is, like, if we actually we start from something well typed, throw the types away, and then run it anyway, we'll land in the zone of things which work.
Yes. So let's try to state this. So what do I want to say? I want to say that this double pipe thing is correct. Let's just say correct. So what do I have? Well, I need a type because I have a typed expression and then an expression of that type. So I'm going to write it like this. If I have a tx per t, then, well, I know how to evaluate E. Mm-hmm. Oop. Okay. And now I want to say that it's the same as evaluating the erasure of E. So if I write this, I have a maybe val, but here on the left-hand side, I have a t val of t. So we have some kind of mismatch. So to even be able to express this notion of equality, we need to express what it means for t val to be the same as a value. But we can do that.
Yeah, let's write a forgetful operation for t vals. We've got one for expressions.
Oh, sure.
You can't quite call it the same name,
V.
but yeah, fair.
So if I have a t val t, then I can get a val. Oop. So v.
Right, and you're almost certainly going to have to make t explicit locally, hilariously.
Yeah, so what I want to do here is match on the t val, and if it's a natural number, then I inject it and so on. But of course, I cannot do that because t val was not defined by induction. It was defined by inspecting what the type we're considering is. So to actually take it apart, we need to match on the t. In a sense, it's a bit like a tagless product, like unboxed sum or whatever you want to call it. We know that we have another thing that plays the role of the tag. It's this type argument. So it's kind of weird here. We have this function taking exactly one argument, but we're actually talking about two of the arguments. But because this one is always implicit, at definition time, it's important to talk about it, but at use time, it's not.
We hope.
We'll hope. Yeah. Well. Okay. Yeah. As always. So if I had a natural number, then the associated value is a nat v, and otherwise it's a bool v. Right. So here. Oh yeah.
Yeah. So now you need to
goal.
say.
So here the goal is a t val, but I have a maybe val. So it tells me that I need to modify the left-hand side because I know how to cast a t val to a val, but not really the other way around. Although I guess I could have done it the other way around also,
Yeah, but this way is nicer. You want to say, it's good to put that just there that you're about to type.
Yeah, I want to write it the other way around.
Fine.
T val v, and then the erasure thing, right?
Yeah. So yeah.
Oh.
Yeah, so we're saying, yeah, we're definitely going to be get one of the evals that works, and it's going to give us the untyped version of the type value. This is nice.
All right. Yeah, maybe that's good. I don't know. Yes. All right. How do we prove this? Well, we're going back actually to that old game of yours, right? What is it blocked on, right? I mean, it's not like there are very many things we can do. Okay, there's a type we could inspect here. But the definition of erasure is not actually looking at the type. It's only looking at the typed expression. And the definition of t-val is only looking at the expression. And the definition of eval or eval, I don't know, is only looking at the expression also. So you have an overwhelming majority of votes in favor of looking at the expression. The only thing that actually looks at the type is this erasure for values here. But let's make everything else compute, and then we'll see whether we need to do more case splitting to get this to work. So we are inspecting the expression. Again, as always, we're getting terrible names. Then we have B, L, and R. Oop, oop, oop. In the base case, so T eval of a natural number, if you remember, was returning directly the natural number without tagging or anything, because the type was known to be nat, so T eval was evaluated to literal natural numbers. And on the left-hand side, we erasing nnat to nnat, and the evaluation of a nat is just yes. Indeed, a nat n. So our goal is trivial. And it's the same thing for bool. For bool, because everything is known statically, it just reduces to bool. If we have a natural number, ooh, should I? I'm tempted to lift it to the top level, but
I mean, there are lots of ways to skin this cat. It's tempting to do rewrite with recursive calls.
Yeah, I quite like doing this also. Let's see.
I mean, you could also do the equational reasoning thing, but
yeah.
But rewrite would be plenty here.
I mean, it's quite nice also to have like the plus V and then plus correctness on top. But anyways, let's just do rewrites. It will be easier.
Have we seen rewrite yet?
No, I don't think we have.
Well, it's no time like the present.
Yes. I think that should do it.
Yeah.
So whenever you have an equation, you can use rewrite, and it will replace in the goal the left-hand side of the equation with its right-hand side. So it will automatically look for all of these occurrences in the type of the goal and substitute the right-hand side. So here, if we look at the new goal, oh, it is somewhat
but you know, keep on trucking.
Yeah, right, it has reduced already.
Yeah. We're just stuck on the next eval now.
Yeah, let's look at this goal first. So if I do a lot of normalization, because we just had plus V, but plus V is actually this nested calls to all of the binds. So you can see that we're stuck on this eval M here.
Yeah.
But when we rewrite by pipe correct,
we want those things to be unstuck, and the way to get them unstuck is to get justs in the right place.
Yeah, exactly. We replaced eval of M with just T eval M, etc. And because we have a just, the bind can now reduce. It's defined by inspecting the first maybe thing. And so now we can do another rewrite. Oh. We're seeing that we're stuck on this eval of the erasure of n. So we just deploy the fact that erasure of n is correct. And I mean, okay, through enough evaluation, it actually gets to something trivial, and we're done. Okay, so
word of warning, in some particularly gnarly situations that we are nowhere near arriving at here, when you just naively replace the left-hand side of the equation by right-hand side of the equation in the goal, what comes back might not be well typed, in which case, if you try and rewrite, you'll get an inscrutable error message.
Talking about W for some reason.
Yes, AGDA won't do anything stupid. It's just that this rewrite move that you wanted to make will turn out to not work. However, we are nowhere near the level of complexity where that kind of thing goes wrong.
Yes. So this rewrite is not actually magic, right? You could write it yourself. So let me comment this out for a bit. Oops. Up.
Okay, it is actually magic. It's just not new magic.
Yeah, yeah. So what did I say? I said that eval rewrites was taking the left-hand side of the equation and replacing it with the right-hand side. Well, we already have a mechanism to abstract over an expression somewhere in the goal.
I don't know if we've actually seen this yet.
Width?
Have we seen the magic power of width yet?
Oh, maybe not.
Let's look at the magic power of
Have
width.
we only seen width as a way to introduce more assumptions in the context, maybe? But width is actually more powerful than
Width
that.
has a second superpower.
So if I use width on eval, well, let's call it W for
for authenticity.
yeah.
Right. You see, it's not only that you bring the thing over to the left-hand side where you can match on it, it's also that you abstract occurrences of the expression you picked from the goal so that when you pattern match on it, you get more bang for the buck.
Yeah. Otherwise, you would have no benefit from dependent pattern matching. But the whole point is that when you observe that something is built using this type of constructor, more things can reduce.
So again, this is something that you never get anywhere near with case expressions.
Yes. So, yeah, okay, let's see. What did I want to do? Oh, yeah, I want to do that.
So you need to
so we got our hands on a name for this expression, but we don't know that it's equal to just the eval of M, right? So the way to do that is to, I can't remember, I can never remember which way around it is, but
it's
let's try it this way.
I'm slightly disturbed. The one in the middle should be a pipe.
Yeah, so
an actual pipe.
This is a pipe. This is not a pipe again.
Why is it green? Oh, it's because of
because I just typed it. I haven't reloaded.
It'll
yet.
turn black in a minute.
Yeah. So let's reload. Oh.
You need.
Oh yeah. EQ.
Right.
All right. So haha, drum roll.
Yes.
Oh, and if I scroll down a little bit, we can see here that we got our call to pipe correct, which says that eval of the erasure of M is equal to just, etc. And because we also abstracted over eval of the erasure of M and called it W, in that equation, it's showing up as W. So not only did it abstract over pipe correct, it also abstracted over like that name here.
Yeah, and it pulled the occurrence of eval M out of the type of this equation while we were at it. So now we're in a glorious position to.
Oh, no.
So you hit
the wrong one.
You hit EQ. Yeah. Now you can pattern match on EQ, and it pattern matches as REFL, and then that substitutes out the other side of the equation.
Yeah, that equation was really well formed, right? It was a variable equal to an expression, so that can always fire. So it will fire by substituting the expression for the variable. Okay.
So this match on left-hand side of equation together with proof of equation, then pattern match on the equality proof as reflexivity to get the substitution to happen. That's a kind of a very frequently occurring dance, and this is just what rewrite desugars to. So that's the fact that there's a coordinated strategy here of choosing these two particular things and then that pattern match. That's worth having its own name.
Yeah, and we use it so often that we just cannot be bothered to write it explicitly. Okay. So now we have more stuff. So we turn the if into the semantic version of the if then else, both on the left and the right hand side. And if we do a bit of normalization, we can see that we might get away with. We might need to do all of them, right?
Yeah.
So we are stuck on this one. So let's rewrite with this one. So I know that
there's a fun thing you can.
So now it has reduced, and we have Do I need to do a case analysis?
I don't know.
Hmm.
I mean, you could try the obvious
Oh,
first
shit.
and see what goes wrong. I mean, if you're lucky.
What's the obvious?
So the
Oh,
obvious
just
is
doing
just to
all
do
of the
all three
rewrites. Yeah.
rewrites
Boop, boop.
and hope. Right.
Well, all
If
right.
if you know, only if this doesn't work are we
Right.
going to try to be clever.
A.
But I suspect
Well,
it
let's
doesn't
try
work.
it. Raffle. It doesn't
No.
actually work
Okay.
because. So if we look at the definition of FV, it was a long time ago.
Yeah.
We can see.
It doesn't do the if until a lot later.
Yeah. Oh no, I know, because so this only reduces when the boolean is a value that we know, right?
Yes.
But the problem is that we don't know what the value is here. So for the natural number, it worked because we knew that we got both a nat on both sides, and then the plus v was peeling off these constructors and then performing the addition and repackaging it on the way out. But here, and this is what this is doing, right? So we have the act. They've made the goals like more intelligent, but as a consequence, now if you click on something, it just jumps to the definition. So now we have the actual f performing the check here with the erasure inside versus the erasure on the outside and the f internally. So what it tells me is that I want this t eval b to compute to something, either true or false. And this way, this internal thing is going to reduce to either this branch or that branch. And this outer f here will go away and return either that one or this one, which is exactly the induction hypothesis.
Yeah. So you got two choices here.
Mm-hmm.
Well, you got more than two choices here. Right. I mean, one of them is to grab T eval B.
Yes, that was going to be my move.
But I would think twice before doing that, because you can see the trouble is that we've got some, okay, maybe this is, what we've got here is an F, I'm not crazy. I'm absolutely not crazy. There's a general fact about ifs, which is that if you've got the same function at the outside level in the then branch and the else branch, then that function is going to happen. So you can float it outside the if. That's just a useful general reasoning principle about if then else.
Yes, so let's see.
And that would get us home here.
No, it just is A to B, right?
Yes.
So B, or maybe I need B to be explicit.
Yeah, you want B to be explicit.
And maybe these ones too, who knows?
Yeah.
Up, up, up.
And then you want to do it.
So I want to say that, well, I need parens anyway.
Yeah,
so if B, then FL, else FR is the same as F of FB, then L, else R.
Yeah, I think this is just a library fact worth having.
Oh. Okay. All right. Okay. And this is exactly that, yeah. If Kong of the thing that takes just erase value V on T eval B. All right, let's see if it can, yes. Just through solving the constraints, it's able to find it.
Yeah.
Right,
so there are, we could have inlined that move if we'd been cunning, but the problem is that with after rewrite is never a good idea. unless they fixed something.
Oh, yeah. I mean, let's have a look at it.
Yeah.
So this is the library-based solution. So you define your Wii auxiliary function. The other one, if you're in
Oh, that's all right, actually.
Well, it's on the case splitting.
Yeah.
But it's a good thing to see, I think. So we're almost there. Both of them are stuck on the V, and we know that as soon as it becomes a value, everything's going to reduce, and we're going to be in a good place. But if we match on this,
then we get an unbelievable pile of vomit. Which
it's vomit that's shaped like this thing
yeah.
that's commented on, right?
Yes.
It's
it's just revealing that that is in fact what it did.
It's a left-hand side with a raffle and so on. So there's a bit of a leaky abstraction here. But if I clean this up through the magic of editing, we're in a good space. So the rewrites literally are with functions. It's just that someone needs to fix that problem. Oh.
Yeah. There is another sneaky way of doing it, which is to do long form with.
Okay.
Except that as well as abstracting eval b, you abstract t eval b at the same time.
Do you want to do it?
Yeah, why not? Okay. So instead of kicking off with the rewrites, well, actually, yeah. Oh, what did I just do? I did the wrong thing. How do I get, okay, good. That's my favorite trick, actually. So, okay, let's comment that out. Okay, I want to be back here.
Oop.
What have I done?
Oh, it's me. I left the equal point.
Okay, so we're back where we were. We look at this goal. And we look at it hard. And we see that on the one hand, we're going to want the induction hypothesis, but on the other hand, we really are going to want to know what T eval B is. So, fine. I'm going to say with, and I want to know what eval I'm going to try typing backpipe B, and then this is a regular pipe, and then T eval B. So I put them both here, and then I do.
Yep.
Oops.
Yeah, so when you're in Unicode input mode, you can press space to exit it and then backspace to come back to it. It's a bit annoying, but.
So what I'm saying is, so this is a slightly different variation on the long form width. Let's see what's happened. Oh, I shouldn't have picked V. Oh no, it'll be fine. Right. So, so that's my eval B ready to hopefully be adjust. But I also grabbed T eval B. So now in the type of the equation, I'm abstracting both eval B and T eval B, which is why my equation says U is just a bool V. So this is a slight variation, even more kind of abstracty than is usually going on with rewrite. So let's see what happens now if I say Q. Then I get that thing. But the good news is I'm now in a position to say, let's look at V to find out what case we're in. And now something cool happens. Okay, maybe it's not that cool. But you can see that is just the induction hypothesis for the right-hand side. So
we have a lazier proof. We just in time decide which one we want to.
yeah. Oh, except that my fingers don't work.
Control C, Control B.
Yeah. Right. Okay. So let's just make sure we're back in color. So that's two flavors of width at once, right? It's really not unusual. On the one hand, to grab something that you also know an equation about. It's also useful just to grab a thing you need to look at. Yeah. But you know that involves a degree of subtlety that perhaps we should only deploy if we're in much greater trouble than we were in for this problem. I actually like our first solution. You know?
Oh, with the IFCON. Yeah.
Well, you know, just step one.
Yes.
I mean, it strikes me, right? It strikes me that rewrite by induction hypothesis is a no-brainer.
Yeah.
You only switch your brain on after you've done that to try and figure out, okay, what algebra is left that is going to get me out of this problem. And that seems like an extremely respectable piece of algebra that we, you know, that we pulled out from
Okay, so
essentially what ought to be in the library.
No.
So
Kerning solution, and then
that's
this. Then I'll comment out this one. And then you have the alternatives, all of it in the source file. Okay. So now we are really happy. We said, okay, if we have a typed if we start from a typed expression, we can forget about the types, and then the evaluation function will behave the same. But can we ever get a typed expression?
Yeah.
Like,
where do they come from?
for all we know, you get an expression, and then it's never possible to produce a typed expression. And then what's the point of this? Right?
Well, expressions didn't type themselves.
So this is the second notion of correctness, in a sense. We can express what it means for an untyped expression to be like secretly typed by actually giving the evidence showing that it is a valid typed expression. Oh, do I want to do this, or
I wouldn't do it that way.
do you want to do with the type as a parameter? Or as a relation?
So I would do it. Do you want me to do it?
Yeah, because this old version is in the archive, so you can always have a look at it. Right?
Yeah.
So let's try to do something different.
Yeah. So what I would do is I would define a funky data type.
Oh, view.
Yeah. I'm gonna talk about expressions I like. So that's to say, and I'm going to define what it is to be not just any old expression, but the kind of expression I like. And of course, I like types, which says for all t in Thai and e in text per t I like the erasure of E. Right? Does that seem like a particular kind of prejudice that we might be into? Anyway.
So this is exactly what we said you shouldn't do, right? Add computations in the return indices of your families,
yes.
because that makes unification really hard.
Right, but the whole point is
That's the
that we
general
only
lesson,
we
and
only
then-
ever use these things when we don't know the index. That's the whole point.
yeah.
Yeah. So
So there are exceptions to the rule.
try
Never do it
liking
unless it's one of
says
these
for all
cases.
E in X bar,
Mm-hmm.
maybe I like E. And here I've made a particular choice which might not be a good choice to box the type on the inside.
Yeah. Yeah, this is what I did mine originally.
But it's it's possible.
Mm-hmm.
Right. So let's see what happens. Well, what are we going to do? We'll discover that we don't have quite time to do it all, but we'll get somewhere. Right. We might well find... Okay, well, we've got nothing. There's no game in town other than looking at the expression.
You could return nothing.
Yes, it's true.
Universally.
Oh, dangerous fingers. There should be R. Okay. So what happens? So here, I'm going to say just question mark auto.
Nice.
And there was no choice about which one it could pick, because the only typed expression it has to pick a type expression that erases to the expression we started with. Right? So we're not just saying, oh, here's a well-typed something that's got nothing whatsoever to do with the program that you put in. This only works if the program that was the input is the program that you have found the typed version of. So here, I'm going to say just again, and also auto, and that's fine. Okay. So now let's see what happens. I'm going to say with try liking n pipe try liking am both at once. Give me a pair of answer columns. I'm just going to call them X and Y. Okay. And we're going to look at X. And if we get nothing, we're just going to fail.
This could be a catch-all.
It could be a catch-all, and it probably will be in a moment. In fact, let's just get there. Yeah. So far the top line is the happy path. Everything else is cheese. Let's keep going. Right, and this is thank you for renaming my renamings.
Well, you didn't reload in between, right? So
oh, that's fair, actually, yes. Okay. Oh, sorry, my bad. I should have said just and then as you suggest, everything else is crap. Right? Right, and let's play the same game. And I'm going to do a dirty trick. Not that dirty. Try liking B. Try liking L. Try liking R. X, Y, Z. Alrighty. So we look at X. Right. I'm just going to install the catch-all now. And then I'll be able to delete rubbish. Okay. Right. We look at X. We look at big T. We don't like that one. Gonna call this B prime. Okay, on we go. We look at Y and Z, and we get a pile of garbage that we want to get rid of. We've got X and Y. Alrighty, now we look at X and Y, and we get some types. So this is T, L, I'm going to call this big L, little L prime, big R, R prime, and I should tidy up, but not just yet. Okay, now I'm going to look at these two types, L and R. What's going on?
Oh, you need to
I need to reload. Right, and now I get a bunch of crap, but I'm going to delete the middle two. And here I'm going to say just query, just query. Oh, what do you reckon to that? So I folded it in the business of checking that the two types in the two branches were equal. So what we're basically showing is that we can do enough testing to crank the erasure map backwards. Yeah, so this this technique, we call this building a view. So this is a view of Expra. We've basically said that, although Expra was born with constructor case analysis, we've now got a new kind of analysis for Expras that we can use on the left-hand sides of programs, namely, are you well typed? And if so, what type are you? So that's one of the joys of dependently typed programming, is that there are ways of seeing that are not the ways that data types were born with. They're programmable, sophisticated ways of seeing, and type checking is one of them.
Yeah, so in particular, you can do something like this, right?
Yeah.
I like types.
You need a just on that.
Yeah. Just group. Just high. And otherwise nothing. You can see that here, instead of like going through the whole expression and trying to do the inference, you can just say, well, did X like arise as some kind of like secret typed expression that was erased? And if it was the case, then I can have the type readily because I know what kind of typed expression it was before.
Yeah, but this type of infer, right? I mean, you know, the type alone doesn't make us a particularly fantastic promise. It just says, well, maybe I can give you a type. It doesn't say that type will have anything to do with the expression.
Yeah.
You know, here it does.
Here we're saying exactly that this is related. Yeah.
Yeah.
And Otto, just like I was really eager to just use nothing on the right-hand side.
Yeah.
And that's because nothing is always free. But we saw last week or 2 weeks ago, decidability, right? So instead you could say, I can decide whether I like this expression, in which case in the unhappy path, instead of returning nothing with a catch-all, you need to prove that no matter what type you might have guessed, there's no way a typed expression of that type would have delivered your original expression through erasure.
Yeah.
For instance, because it's not well typed.
And even better would be to cook up a data type that represents an expression with a detectable type error in it. So that's to say, you've got an opportunity here to say, well, what actually are the meaningful error messages to give back when typing fails?
Yeah, you want to point precisely to the source of the error. All right.